Good evening, and thanks for joining tonight's TI Technology webinar hosted by Texas Instruments, where tonight we're going to continue in this is now, I think, the third part in our series of teaching topics effectively. If you missed the other two parts, don't worry. These parts are all independent of each other, and you can always visit our website to pick up the other previous on-demand webinars. So tonight we're going to check out domain and range of functions in algebra through calculus. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI technology to make tough-to-teach, tough-to-learn concepts accessible to all my students. Tonight we're lucky to be joined by our two panelists, Diane Broberg and Ray Barton. Diane has been teaching high school math for over 30 years. She served on writing teams for Texas Instruments and taught many summer workshops. Making math come alive for teachers and students keeps her creative. Outside of math, she's an avid runner and baker. Diane, thanks for joining us tonight.
I'm glad to be here. Welcome, all of you.
And Ray has been a T-Cube national instructor for many years. He currently teaches AP statistics and middle school algebra and has helped develop many T-Cube workshops. He enjoys using graphing technology to make mathematics accessible and interesting for students. He teaches at the Waterford School in Salt Lake City, Utah. Ray, it's also great to have you with us.
Well, I'm excited to be here tonight.
Ray, would you do me a favor and talk through our agenda tonight?
Certainly. So tonight we're going to be investigating domain and range, and we're going to begin by seeing what domain and range will look like on composite functions. And then Diane is going to show us how to do piecewise functions and the implications for domain and range there. Then we're going to look at a great Nspire document called Dynagraphs that perhaps might be new for some of you. After that, we're going to look at some applied problems using graphs and the solve command, I believe, on the Nspire, and see how domain and range factor into kind of real-world problems. Then we're going to look at another TI-Nspire document, an activity called Exploring Domain and Range. That is a really neat interactive document that helps students to visualize domain and range for various functions. And if we have time, we may even get to parametric equations and possibly discrete functions. We'll just have to see how that plays out.
Ray, thanks so much. And Diane, will you talk through our expected outcomes?
Sure. We're hoping that at the end of the night, you can help students visualize domain and range graphically and also use numerical representations to investigate domain restrictions and the implications for range. We're also hoping you can use either the Nspire CX2 and the 84CE to explore functions, domain, and range. And finally, we're hoping that you can look at some of the applications and the restrictions and how, the implications that has for functions. We're hoping overall that you have a good connection with functions, domain, and range by the end of the evening.
Perfect. Thanks so much, Diane. Thanks also to everyone who completed our short 5-question survey. It's still open if you haven't had a chance to complete it. You can find it under the polling tab. The session is being recorded, and we'll provide a link to the event certificate of attendance at the conclusion of the webinar. We'll also be using the chat window to send general messages, and you can use the Q&A window to send any questions to Diane or Ray at any time. So with that being said, Ray, let me give you control. Feel free to share your screen.
Okay, thank you. And while I'm getting that screen share set up, I wondered if I could throw a question out to our participants and to Diane. As you teach domain and range, what are some of the difficulties that our students encounter, and what might make it difficult for us as teachers to be able to teach domain and range? And we'd, of course, love to hear some responses from our participants in the chat window. If you can put something in chat, we'll take a look at that. And while we're waiting for you perhaps to respond, Diane, what kinds of things sometimes are hard for your students, and kind of how does a typical approach go with domain and range?
Well, one of the things I find always interesting is when students go to graph a function and they graph something on their calculator that they know they're supposed to be able to graph, and the first thing they say to me is, Mrs. Brover, the calculator doesn't work. It's not here. And I think that's such an interesting conversation and a window into what domain and range are. And so we have this conversation that starts out with with graphing, is the function there? What does domain and range mean? And how do we see that on our calculators? And how does knowing what domain and range mean help us figure out how to visualize it? So that's one of the things that I have a regular conversation with students about, hey, because they always tell me their calculator is broken. I'm sure you've seen the same.
Yep. Thanks. I was just looking in our chat window and I noticed some comments from some of our participants. Jim says they're good with discrete points, but then when we make the jump to a continuous function, that can be a challenge. So hopefully we'll look at a few tools tonight that will kind of help make that transition from discrete functions to continuous functions.
We also have someone that talks about a denominator. When a denominator is, we have a fraction, a rational function, when we have a denominator that is a quadratic, what impact does that have on a graph? That's always something that we're going to spend a little time talking tonight about, is those points where things are undefined.
Yeah. And Rudy says that I think kids have a hard time with recognizing that the points that compose a graph correspond to the domain and range. Isn't that true? And I think we've got a couple of really cool Nspire documents that might help students to make that connection as well.
I like the adjusting the window. We're going to talk a couple little bit tonight about how we can work with students in adjusting the window, because I really do think the more that we can have students think about adjusting the window, that really is, hey, do you understand what domain and range is? My students like to, after they figure it out, like to hit that zoom fit. And sometimes I'd like to have more of a discussion than a zoom fit.
Great. And a comment from Prudence about students struggling sometimes reversing the order of domain and range, and of course, appropriate window that we just talked about, and piecewise. So we're going to definitely take a good look at how to do piecewise functions on both platforms, on 84 and on Nspire. So why don't I share my screen, and we're going to start out by doing a composite function on the 84, and we're going to do it in the context of an ACT question. So I'm hoping, can you all see my my computer screen now with a PowerPoint slide about a composite function?
It looks good, Ray.
Thank you. So this is a question off an old ACT test. Two functions are defined below. What's the domain of the composite f of g of x? And it looks like the outside function is root x minus 1, and the inside function is the cube of 2 minus x. And then there are some choices there. So we're going to see how this might look when we tackle it on TI-84. So now I'm hoping you can see my TI-84 emulator. And so in Y1, I'm going to place that inside function. So that would be in parentheses 2 minus x raised to the third power. And then in Y2, I'll place that outside function, which I think was root x minus 1. And then the composite would then be Y2 of Y1. So one way to get the Y2, I could hit the vars key, as you can hopefully see it in red on my emulator now, and go over to yvars, and then select number 1 function. And that gives us a list of all the y variables, and we wanted to select Y2. And then another way to do that, another way to access the y variables is to go alpha, and I think it's trace up here. And that brings up a quick pop-up menu of the y variable. So then I can select number 1 to get Y1 there. So hopefully there's our composite. And for a window, I'm going to go from -1 on the x over to 4 with a scale of 1. And then for y, I'm going to go from -2 to 3. And then something I always like to do with students before I ever hit the graph key is ask them to try to predict what they're going to see. So if, they're not going to get all the pieces, but it would be wonderful if they could get some pieces. I'd love if they say we're going to see 3 graphs and then start thinking about the shapes of the graphs, at least the first 2. So I try to have them sketch before they hit the graph key. So it's just to start thinking about it. And after they've had a minute to do that, then we can go ahead and graph the function. So there's that cube, and then the square root, and then last of all, the black one. So at this point, I wonder, I'd love to hear from our participants, what questions at this point might we ask our students? So if you want to pop something in the chat window, or just be thinking about that, or there's some good questions we could ask our students now that we've got this visualization to move the dialogue forward.
Rudy's got the question. My students, I would hope would ask, hey, why does that black graph stop?
Yeah.
Like, where'd the rest of it go?
Yeah, it seems kind of abrupt, doesn't it? And so we know that the black function is the composite. If we go back here, the reason I know that, by the way, if I go back here and look in my y equals menu, I've got the colors off to the left. So I know that y1 is blue, that's the cube, and the root function is red, and the composite is black. So our black function is the composite, but why did it stop? Kind of an abrupt stop there. So one way to start thinking about this is to interact with this graph and see why some values don't end up showing up on the black graph. So I could trace, and I'm going to try and pick one, first of all, that does work, that does end up on the black graph. So I'm going to try 0.8 for the x. And when I do that, I notice that y is 1.728. So the input for the blue function is 0.8. The output for the blue is 1.728. And now I want to take that 1.728 and use that as input for the red function. So I'll jump down to the red function and type in 1.728. And I end up with the final value of 0.31. And then I might ask my students, so how could I end up at the same y value on the composite function, on the black one? So if we want to trace on the black function, what should my input be? And some of them might think, well, the input should be 1.728 because that's the input I can see down here. But if we try that, so I'll jump down to the black one. If I try that, see right now I'm at about 1.728, and that didn't give me the right y coordinate, the 0.31 that I had. So hopefully they realize we want to go back to the beginning and use the same input that I started with on my blue function, which was 0.8. Then let's do one that doesn't work. And by doesn't work, we mean we'll start out on the blue function, but we're not going to be able to end up on the black one. So I'm going to try tracing on the blue one. So I'll go back up to the blue, which is that inside function. And I'm going to try 2.5 for my input. And that jumps me over here. And now my output for the inside function is negative 0.125. And then I want to use that as input for the red function. So I'll jump to the red function and go negative 0.125. But there's a problem there because we see the red one doesn't extend over into negative territory. That's all a lot to keep track of. Somebody, I think I just saw a comment pop up about perhaps hiding the inside and the outside function so that we just have the composite function. So you can certainly hide functions if you feel like that might be to your advantage. I think if I go over here on the equal sign and press enter, it would unselect it. And I could unselect that one. I think this was the suggestion that was made in the chat window. And then just have the composite to focus on. So that may help clarify what you're trying to do, or you may still want to see them. I'm going to turn them back on and then just show one more way to try to sort of visualize what we just did.
This is a really cool thing that Ray has done. It kind of made like compositions come alive for me. Check out this method instead of hiding them. See what you can do.
Yeah, actually, I just realized before I do that, let's go ahead and do it now. So we did a lot of tracing, but points kind of disappeared when we when we did tracing. We jumped around, and a point we had a minute ago on the blue function is now gone. And so you can use the draw feature to sort of keep track of everything. So I could use the draw command to move around and keep track of where I've been on all the trip, the tour that I made through all these functions to end up on the black one. And a way to help facilitate that, I'm going to add one more function. I'm going to add y equals x. You'll see why we're doing that in just a minute. So the reason I'm using y equals x, we're going to do something that's kind of like it reminds me of a cobweb graph, if you've ever done those, with kind of some chaos theory and cobweb graphs. So now I'm going to use the draw feature. So I'll go second, and then the program key has draw above it. And I'm going to draw a line. And I'll hit the graph key because that lines up with that style tab. And then I think I can change the color. I'd like a different color than any of my graphs. So I'm going to go green. And then I'll do that tracing again, but with drawing. So remember I start on the one that worked. I started out at about 0.8. So I don't have a perfect window here, but I'll get as close to 0.8 as I can. Got a little too fast with my mouse there, but that's about as close as I'm going to get. Then I'll press enter to mark the bottom of the line. Then I'll go up here to the blue graph and press enter to mark that line. And then notice my y is about 1.72, 1.73 is what we had before. I'll press enter again. And now I want to use that 1.7 as input for the red one. But an easy way to do that is to draw a line. Instead of going down to the x-axis and over to 1.7, I'll go over to my line y equals x. And if I do that, since x was 1.7, then y should be about 1.7, about 1.728. And now I can just go straight down to the red one. And so that kind of keeps track of all of that tracing and input and output. So there's our final y value of 0.317. So it's sort of a way to visualize this idea of the input for the inside function gives us an output, which is up here, which then we go over to the y-axis, and that becomes the input for the red function. And there's our final result. And what's more, if I forgot to press enter to mark the beginning of my line. Let me get back over there. I want to get back to that point. I have to press enter to mark the beginning of the line segment. And then when I drag, it leaves the line segment with me. So it's no coincidence that we end up on the black graph at the same place where the first vertical line went. So it's a way to kind of visualize. You see why I said it reminds me of a cobweb graph. So we see that if I start at 0.8 and go up to the blue one, over to y equals x, and then down to the red one, and then back over to the black one, which is the composite, I get the same thing as if I'd started at the same original point and just go straight up to the black one. I think and then I've just got a real quick Nspire document that's a little more dynamic. But another way to tackle all this is with tables. And so we can show the input, this idea of input into the inside and output to the outside function, input to the outside function with a table. So I think I'm going to clear this see if I can clear our lines. And I think I also want to get rid of that y equals x because I don't need that on my table. So I'm going to delete y equals x. Go back to the graph. And now I'd like to split the screen and have the graph and the table. So I think I can go to mode. And there's a feature down here that lets me split the screen with a graph table. And I think for this one, it might be easier to have a horizontal split so that we can see several functions at the same time. And now if I hit the graph key, excuse me, I've still got my functions up top, but I'm going to have a table down below in just a minute. And I want to set that table up. So I'll go second table set, which I think is above the window key. And what I'd like to do is use the ask feature for both so that instead of automatically populating all the columns, I can just see the ones that I want to see. So I'll choose ask for both. And now if I go second table, that should jump me down here to the bottom split. And now I'm just going to go through that kind of tracing feature that I did before. I think my original input was 0.8. And notice that nothing happened in the Y columns because I haven't asked for it yet because I don't want to see them all. I just want to see Y1. So if I go over there and press enter, then I see that if X is 0.8, the output for my inside function is 1.728. And then we wanted that to be the input for the red function, which is the outside function. So I'll put that in for X here. And now I can go over to my outside function and press enter. And there's that 0.3145. And then last of all, how could I get 0.3145 in my black function, which is the composite? Well, remember, students, that we need an input of 0.8. So I'll go to the top row and go over there and just press enter. And then notice we've got the same output for Y3 that we do for Y1. So that's sort of a numerical way to try to keep track of all of this inside and outside and the composite of a domain function. And then just one last thing quickly, going back to that cobweb sort of graph, I set up the same thing on an Nspire document, but this one's dynamic. So here's my original input, which is around 0.8. We went up to the red, up to the blue one to get the output and use that as input by going across and down to the red one. But now I can drag this. And so what would happen if I drag too far? Right now it's still working, but if I go a little too far, then the whole thing disappears. So you might be able to have fun to use this as a demonstration tool. So that's kind of an interactive way to deal with that idea of composites and domain and range. So I think now, Diane, I'm going to pass it over to you and we can jump on to our next example.
Yeah. So Ray, thank you for that. I think that was really interesting to listen to watch the chat. I think people noticed a couple really cool things for all of us. Is that one, his drawing the vertical and horizontal lines. It took people a couple seconds, but then they realized, hey, that's the input and the output. And I think sometimes as teachers, we do forget that we need to stop and help students walk through this concept of the input and the output. And then to do it again using the ask feature on the table. Many teachers have done ask for the input, but they haven't done ask for the dependent variable. And so this allows you to see both those things together. And so this was our first example of looking at domain and range, and we looked at it graphically. We looked at one of those hard to teach things. Composition of functions is really hard for students to understand. And so this is one of those hard to teach things that gives you a couple other ideas of how you can look at it. So then we're going to jump. One of your other things people asked about was we asked about thinking about piecewise functions. And so we're going to look at piecewise functions a couple different ways. And so first we're going to look at it, we're going to try to look at it both on the Nspire and on the 84 because they are very different. And there's some new things that have come with the 84 depending on how old your software is. So we're going to try to graph a piecewise function. I'm going to show you a couple of my favorite things. And so let's go to math. And most of you, when you look, oh, first I'm up in y equals, because we're going to graph it first. I think one of the things we often have to look at is like, how do we graph a piecewise function? So let's look at it first from a graphing standpoint. So if you scroll down, you will see right here, there is a piecewise template. Now this is on, if you have the 84 plus CE version, there is a template for a piecewise function. And when you click it up, you have your choices. What would you like it to be? Well, I think I would like, I got to move Ray here for a second. I would like to have, I think I'm only going to go for 2 pieces. So I'm going to go back to 2 and then I'm going to click OK. So notice my template gives me my function and my domain. So I'm going to start by graphing some functions that maybe you have graphed and maybe you haven't. I'm going to use my math template. This time I'm going to go to number because I'm going to graph the absolute value. And I'm going to graph the absolute value of x minus 2. And I am going to graph that when my domain with x is greater than or equal to. So you may remember to find those keys, you need to hit second and math or test. And you can find your greater than or equal to. And I would like it to be greater than or equal to 1. And now we're going to go back to the second piece. Now you're going to get my absolute favorite feature of the calculator. Now, all of my students will tell you, if you ask them what is Mrs. Brobert's favorite thing, they will tell you alpha y equals, because I love the template for the fraction. Now, there's a second way to get that we'll do in a few minutes, but this is one way to get it. X squared, and I'm going to do x squared minus 1. And because I wanted the fraction just for you all to see it, I decided I would divide it by 2. The sole reason was so you could see that function. And I'm then going to graph with x is less than 1. And as most of our students do, we have a couple options. I'm going to start, and I'm just going to hit zoom, and I'm going to do zoom standard for now. It doesn't give much thought to it, but it does give us a graph. So what are some of the things we want students to think about this graph?
So Joshua said, if you were to do -5 less than x less than 1, would it be done the same way in inequalities? And then Sam mentioned we might want to talk about the values at the endpoints. Rudy says, is it a function?
Yeah.
We could ask students, is it a function? And Jay says, of course, we could talk about discontinuities, especially, of course, in a pre-calculus class or a calculus class, but certainly in other classes, we can talk about discontinuities as well.
Right. So if we, and this actually makes discontinuities really easy to talk about so that they don't have to wait for pre-calculus. One of the things I think I've discovered over my career is that sometimes we wait until too late to expose students to some of these concepts. When discontinuities, if you could ask students, hey, you know, is this function continuous? Without even defining continuous, I think they could understand what we're doing. But here you saw one of the things is we can trace. One of the wonders is what happens at 1. So if we go right to 1 and we hit enter, we can see, well, it's defined. Well, what happens if I use my down arrow? Ooh, it's not going to let me jump. If I had 2 functions, it would let me jump. What happens, though, when I go less than 1? Then we can see that it hops over to the other function. So all of a sudden, sometimes when in the example that Ray just did with you, we could jump between 2 functions. Because this is one defined function, we can't do that anymore. And so that allows students to begin to discover that it is one function, it is not 2. And so at x equals 1, there is only one value that it can actually be. And I think that is a big distinguishing factors that students struggle with. One of the tests I gave this year in pre-calc, I asked students on a piecewise function, what was f of 1? And many gave me 2 answers because they put it in both functions instead of putting it and realizing it is just one function. They put it in both pieces. Okay, so a quick little template here, something that we can discover as we're looking at these things. Again, we can look at our table, and we can use our table to get some of the different values. But again, what looking at the table stresses for all of us is that this is solely one function instead of being two. And I think that's an important thing for us to look at. Well, what I was hoping to do with this is to show you one of that big things about looking at it and looking at the template that you could do. So if I go back to my graph for a minute, something else that we have looked at is that the ability to save these things. So sometimes when I go into class, I teach a couple different classes back to back. Yep.
Just 1 second before you save that, there were just a couple more comments I thought were great. People mentioned we might want to ask on what intervals is the function increasing or decreasing, which would force students to deal with moving across that piecewise interval and where it switches up. And then Josh also mentions when to access that menu, that template, he likes to go up, scroll up on the math menu, which is, I guess, like going around the horn when you're running your TV remote. So just appreciated those comments as well.
Right, I'll show you that real quickly here. So one of the things, but I have found like sometimes students don't see that as well as we as adults do, that I have very few students that are going to go use the up arrow. Most of my students are going to start at the top and they're going to work their way down until they find it. And so I'm willing to go both ways. I scrolled down solely because I've kind of gotten used to how my students do it now. And they just aren't as comfortable with the scrolling up as I am. So I find it comical what students find easy and what students find hard. Well, so back to my other thought. So one of our things that we get stuck on sometimes as teachers is we have classes back to back, or this is something, sometimes I prepare my lessons on the weekends and try to get everything all together so that the week goes smoothly. I'm a track coach, so right now that's kind of important for me. And so another thing that the 84 allows us to do, it allows us to save these things. So if I go up here to actions, I can, this is called an emulator state. It will save for me my window and my functions that I put in there. So if I go to save emulator state, it allows me to save it wherever I'd like to. I'll stick it on my desktop here, and I would like to call this piecewise functions. And I can hit save. And then when it comes back to my lesson on Tuesday, my lesson is all ready to go. I will then, and in a few minutes, I'll load a different emulator state for you to show you how to load it back in. But at the same time, I also want to show for some of you who use the Nspire, how the Nspire works with piecewise function. It is very similar. If I go to graphs, and this time I'm going to use the piecewise template, which is right next to the book in the 9. It is this piecewise template. There are 2 of them up here. If you'll notice, there is one that gives me lots of pieces. That will give me as many pieces as I'd like. This will give me my 2 pieces. If we enter this in, I'll do a little bit different one this time. Let's do x minus 3. And we will do that. We'll do something different here completely. We will do it when x is less than 1. This time to get your inequalities, you're going to hit control and the equal sign. And we'll do greater than, someone mentioned 5 before, so let's do 5 there. And then down here, we will do 2x plus 1. And this time we will do when x is less than, let's make it less than 2. And as Ray talked, before students can even start this one, it'd be interesting to have them do a small sketch. Have them think about things like, what's the domain of this? How is that domain going to affect your range? And now if we hit, I'm going to hit menu, and I'm going to hit, I'm going to check my window again. I'm going to hit zoom standard. And I forgot to hit enter, didn't I? Where is it? Oh, I didn't hit enter. Okay, you're gonna have to put it. You're gonna have to put it up me doing it really fast now. Let's see if I can do it. I might not remember what I just typed. Oops, I know that wasn't it. It was a 5.
Greater than
Someone said it
5.
last time. Oops, that was not an 11. I got too excited. And this will be x is less than 2. And now I should hit enter, and there it is. How is that an interesting function for students to deal with? How often do we create functions that are not, that yes, we're used to them not being continuous, but again, this one has a domain that's not all real numbers. The last one we did on the 84 had a domain that was all real numbers, which is more typical from our textbook problems. What do you think? Thoughts?
Well, Rudy says it seems like we don't usually give a domain of all real numbers, and I think some of our participants really like this graph, cool looking graph, because it is different than ones we usually do.
Yeah, and I think that's something that we can investigate because we have really good technology between the 84 and the Nspire. We have this technology that allows us to do that versus being stuck in functions that we're used to doing because of how our textbooks happen to portray them to us. Hey, Ray, how about if you try to show them our other, the dynagraphs on the Nspire?
Okay, awesome. This is a fun way to another way to visualize domain of composite functions. So get your mind thinking about composite functions again. And let me share my screen with you. And first I want to show you where you can find this document that we're going to play with, this Nspire document. So I'm hoping you all can see my web browser now. And I'm at a website called Math Inspired, which is just one of my go-to spots for finding great documents. I would say, even though many of our participants probably use TI-84s with their students in class, it'd still be well worth your investment of a little bit of money and some time to also acquire Inspired, even if you just have this Nspire on your computer so that you can use it as a demonstration tool. Then you can access some of these great Nspire documents. So where you can find this dynagraph feature is in pre-calculus, and then go down to functions and graphs. And then here it is, dynagraphs. And when I click on it, there are several things you can download. If you look over in the right-hand margin, you can download all the files in a zip. There's a teacher notes, there's a blackline student activity, and then the TNS document. And so all of those different resources. And so now let me take you over to, so you can see what the document looks like, the dynagraph document, if you upload it. So there are some instructions here. We're going to drag a point to see the dynamic relationship between input and output. So the following page shows a dynagraph. We don't know what the function is though. But so here's the dynagraph on the left. So the green vertical line is the x-axis, the input, and the blue vertical line is the output. And the arrow is the connector that shows that pairing or that mapping from the domain to the range. Then we can drag it. There we go. My computer's a little sluggish here. You can drag it and see what happens with different input and output. And then as you notice over on the right side, there's the ordered pair being dragged back and forth. So you can ask students to try to investigate and see which, what do you think the function is? And then you could go over here and click on the y-axis, and we're just going to zip through this because we don't have as much time as I'd love to investigate this, but I can hit the tab key, and I think it turns out the function is 2x -1. Certainly our students would need a little longer to play with that and figure it out. But then I can click back over on the dynograph and we can see how as I drag the dynograph, those points move along 2x minus 1. Now that one's not a composite. I think I promised you a composite function. So we'll get to that in a minute. But just before we do that, the one more example here. Here, notice, ooh, the dynograph disappeared. And then it reappeared. So what's going on there? You might want to ask your students. And you can see the blue dot disappears and then reappears. So here's one where we've got a restricted domain that students can play with. And then one last one here. Here's a composite. So we've got a third middle bar here. So we have input on the green. So that's the x going up to the inside function, the tan function. And then that becomes the input for the outside function. And so when you drag that, we could see points moving along. So this is a cool way another way to think about input and output, about domain and range, and how they connect to the graph. And I think that's all we'll do with this one. You're welcome to download it and look at the student activity and some of the questions that are asked. But just know that that's there, and that's a wonderful resource for visualizing. And now I think I'm going to send it back over to Diane to do an applied problem. But Diane, I know we talked about maybe doing one or two of them. I think we might only have time. Well, we'll see how it goes, but we might only have time for one. I'll leave it up to you. We'll see how it feels. But anyway, let me send the screen control back over to you.
And as Ray is sending that back over here, for those of you who haven't used some of the Nspire documents, one of the things I think that is really cool and how they're well written is that every Nspire document comes with a teacher document and it comes with a student document. So if you're kind of looking at that dynograph saying, how can I use this in class? If you actually download the student activity and the teacher activity, it will give you all the hints you need. It'll give you the questions that you can ask and how it's designed to help students interact with the math. And so that's been really, really helpful for me when I look at an activity and am trying to figure out what I'm going to do with it. So I would encourage you to do that. When Ray and I first started talking about this, I thought back to a problem that I had done a long time ago. And this is one of my favorite problems to do in pre-calc. It can be done, it actually can be done in Algebra 1. If we think about it in terms of what we're having, or it can be done in calculus. And so it's a beautiful problem because it has all the ways, it's a rich problem. There are lots of ways to think about it. So some of this is classic for some of you. You have 340 meters of fencing, but this time you're going to enclose 2 fields. And they might not be stuck next to each other. And it says you have a rectangular one and it says you have a square one. One field, the square must contain at least 100 square meters. The rectangular one must contain at least 800 square meters. So take a minute. If you have a piece of paper sitting next to you, draw yourself a little picture and think about kind of what's happening here. And it's an interesting thing if we can think about kind of what's happening. And so then the question goes on to say, and so let's see here. I'm going to try something. I haven't tried this, but we're going to try it. We'll see if it works. I'll tell you in a minute if it does. And if not, it'll be bad, but we'll be okay. You'll all be fine. I think I can draw. Here's what's happening. This is what I do in class, is we have 2 fields. There they are. It says one of them, this is X, is whoops, maybe it doesn't want to erase as fast. What did I hit to make it erase? Okay, here we go again. This we decided was Y times Y. And this one is X and 2X. And we know some of the restrictions that have to happen. The small one has to have a perimeter of an area of at least 100, and the other one has to have an area of at least 800. So all of a sudden we have restrictions taking place. We know that together they have to be 340. So the smallest this one over here can be is 10 by 10. And if this is 10 by 10, that means I have 300 meters left for this one. And if I have 300 meters left for that one, and I know that the area is 2x squared. Whoops, let's try again. I have my perimeter 6x. I don't know why it doesn't want to write my x's there. If I have the perimeter 6x, then I know it can be a maximum of 50. And with the other of being a maximum, this has to have at least 800. I know that it has to have, x has to be at least 20. So I now in class, I would take a lot more time to be able to look at that. But what I'd like to do for a minute now is I would like to explore this on my 84. So I told you before that I had a emulator state. So I'm going to go to actions and I'm going to load my emulator state. And I have it saved here as area. I worked on this earlier. And so if I open this now, it says, hey, would I like to do that? And yes, I would love to load it. And the question eventually is asking me to maximize the area of these two rectangles. And so one, the area was 2x squared. The second one, let's make that x squared. The second one, my area is, this is my rectangle, and I'm putting it in one variable. And so I have this 340. But now I had to think about this. What should my window be? Well, we talked for just a brief moment that our window might be between 20 and 50. And that is having me think about domain. So I know if I look at this, I know I need to go between 20 and 50. But if I start out, I should have not told you my numbers down here. I'm going to change them really fast on you. And I'm going to graph it right now. And I'm going to do what my students do. And they're going to be like, Mrs. Broberg, there is no graph. And one of the initial participants said, what I have problems with students figuring out is once they have domain, how do they figure out the range? And so we can look at the table. And students forget this feature, that there's a table here. And so if we look at the table, now I played with it before, and so all of my settings were fixed so that my table was set. I didn't do it Ray's way with the ask and the independent variables. What I did is I went to second in table set and said, well, I know I need to start at 20. And so now let me look at that table and I can look at my numbers. Well, it always bothers students when we have fractions, but I have some nice numbers in between, or what they would say is nice numbers. I have a 3,400. I can see what kind of is happening. And this allows me to think about, okay, what's my range going to be? And if I'd like, I can scroll down here. Okay, looks like we're going down here, 24. Looks like we're going down. Okay, oh, we got a 26. So if I think about it, all of a sudden we have these constraints that have made things different for us. So we have this window we know that needs to go between 20 and 50. And we looked at our minimum numbers, and it looks like we had a 2,000 here. And just to make sure we'll get it there, I'll go back to my 8,000 here. And so now when I hit graph, there's my picture. Well, what did the question ask us to find?
Was it the minimum?
It was asking us to find when is the area a maximum?
Maximum.
It's a maximum. Students look at this and they've done 26 minimization problems and they're like, look, we can see the minimum. The minimum's happening, you know, if I trace here so that you can see my cursor, the minimum's happening right here. And we all want to think about the minimum, but the question you want, if you're putting in a fence and you're going to put a garden and you don't want your deer to eat it, you want to have a maximum area. And all of a sudden, when does the maximum appear? Kind of cool. The maximum is at an endpoint. And that is a problem that is non-routine for students. We get them so accustomed that we're going to, especially as we get closer and closer to calculus. This is a calculus question. You know, every calculus student found the first derivative, set it equal to 0, and got an answer here that was somewhere around 34 or 35. But that's not what the question was asking. The question was asking where maximum took place, and that maximum takes place at an endpoint. And that's one of those questions when I look at it. and say, there's a rich question. It is accessible for algebra. It allows us to think about domain and range in a powerful way, and allows us to visualize mathematics.
Thanks, Diane.
So that to me is a really cool question. Ray, would you like to do the one, show them one more visualization of domain and range?
Absolutely. I feel like I may have saved the best for last year. This is one of my favorites.
It actually is my favorite too. This is one of those activities that I have used every single time I teach domain and range. And I will tell you all, my students are working with an 84. So this is one of those ones when I do it in class, I actually do it as a demonstration using domain and range.
Okay, thanks. So this is another one of those Inspire documents, which you can find, if you go back to Math Inspired, it's under Algebra. And then if I click on Functions and Relations underneath Algebra, then it's here, it's called Exploring Domain and Range. And so I've downloaded it, and this is what it looks like. So I'm just going to take you for a quick tour through the document, and then if you're interested in how that student activity looks, you can download that for some great suggestions about how to implement it with some good questions in class. But we start out with a discrete function, and the instructions were to move point P to each point on the scatter plot. So point P is draggable, so I'm going to move it to, maybe I'll move it up to this point here, and ask my students, what did you notice happened? And maybe I'll drag it over to this one, and again, what do you see happening? And what do you think will happen when I drag it over into the first quadrant? So I'll drag it over here. And so hopefully our students would notice that as I drag that green point around to the different black points, that we're getting a trail of points on the x-axis and on the y-axis. So I think I've hit them all now. So now you think about what questions might you ask your students about what's going on. What are those blue dots? What are the red dots? What kinds of questions could we ask students at this point? So a way to visualize domain and range with a discrete function. And if we go on to problem number 2, got the same idea again, but now it's with a continuous function. So here's our draggable point P, and we might want to ask our students, what's going on? What's the deal with this blue dot? And what's going on with this red dot? But then what's really amazing is how interactive it is. So if I grab this and start dragging it, see how it leaves a trail of where it's been. So we might ask our students more, what other questions could we ask about the red and the blue line segments? Maybe things like, how high is that red line segment going to go? So drag it all the way up to the end point. How low can it go if I go over here to the right endpoint? So a great way to sort of visualize domain and range with a continuous function. And then just quickly, 1 or 2 more minutes, then we need to hand it back off to Michael to wrap us up. So here's a sawtooth function. So you could ask, I can think of some great questions to ask students before I start dragging. And then parabola, again, see domain and range. There's a hollow circle there. It's probably some good questions we could ask about how that connects to the red one. And then last of all, now there are some questions in the student document about, now it's the function that's draggable. So these endpoints of my function are draggable, and we could say, how can we change our function to get a specified domain? So what if I wanted the domain to go from, say, -5 up to or if I wanted the domain to go from -5 to 8 and I wanted the range to go from -4 to 3, then this would work. But say I wanted the range to only go up to 2, then I'd have to drag it down. So we're kind of reversing the scenario here. And now, instead of given a function, find domain and range, we might say, given a domain and for a specific domain and range, could we create a function that does it? So some really just great interactive possibilities there. So we've zipped through it pretty fast, but hopefully you'll be able to download that from TI-Nspire. It was in Algebra 1 and then functions and relations, and play with it and have some fun. I think it's worth getting TI-Nspire or getting TI-Nspire, I mean, just to have this software as a demonstration tool for some of these great documents that people have written.
Hey, Ray, before you hand it back, can I just make one note? Hey, note, all of you, look, it's got open dots and closed dots. What a cool way for us to allow students to think, hey, what do you think an open dot means versus what do you think a closed dot means? I think that's a really, really cool tool. And if you notice, those open dots occur on both the X and the Y axis. And that's just another really cool tool for it to happen.
Yeah. Yep.
So I just wanted to point that out so you all could see it, because I think it's one of those things that we say to students, draw an open dot if it's not included, draw a closed dot if it's included, versus can we say to students, hey, what do you think an open dot means?
Yep.
Do you think that's included in the domain? Hey, let's go back to page 1. And in page 1, all of our things were closed dots. One of the things I have appreciated about the Nspire and the 84 is how good they are at teaching mathematics. That the math I want to teach, I want students to understand that an open dot means it's not included. It allows me to do that quite readily.
Thanks, Diane. And as you can tell, I also just truly love the interactive ability of these Nspire documents, where you create a mathematical object and students can interact with it. And it's just a wealth of great questions you can ask and a good way to visualize. Okay, well, I think it's time to hand it back off to Michael, and we'll wrap up our webinar.
Excellent, Ray, Diane, thanks so much. As promised, we're giving away to one lucky winner a TI graphing calculator. Tonight's lucky winner is David Steingart. So, David, congratulations. We'll be in touch over email next couple weeks to get some information from you. But start thinking about which TI graphing calculator you'd like to choose. To receive a certificate of attendance, go ahead and click the link in the chat window. Also, list is link for the certificate and the documents. And if these links aren't working for you for any reason, just hang tight. You'll automatically get a follow-up email within a couple of days. And that follow-up email will contain links to the certificate, the documents, and the recording as well, so you can watch this at your own pace. And if you're watching this on demand, go ahead and copy that link into your favorite browser to receive your certificate. After the webinar, if you're in need of any help, feel free to give us a call or send us an email, 1-800-TI-CARES, or drop us that email at ti-cares@ti.com. We'd love to hear from you. Speaking of hearing from you, when you leave the webinar tonight, a brief survey will automatically appear in your browser. Your feedback really guides us as we plan future online events, and we really hope you share your thoughts in that post-webinar survey. Huge thanks to Diane and Ray for everything you put together tonight. Just looking through the evening here, I saw lots of, wow, that was cool, I didn't know it could do that, or that's a great way of visualizing it. Lots of, I think, already positive feedback. So huge thanks to everything you guys put together tonight.
Thanks for having us.
Thank you.
And even bigger thanks to everyone who joined us tonight.
Yes.
Stay safe. We hope to see you back online next week. Have a great night.
Okay, take care.